So hello everybody, and good afternoon to you all. I'm just going to turn off my camera because I'll probably be dancing around a little bit on the screen. So let me just turn off my camera, but keep the microphone on because no one wants to pay attention to me. They want to pay attention to the actual screen. So thanks to Alex and the collab team for providing this platform, this collab platform, which is fantastic, and for inviting Building Research Solutions to be part of this movement. So I've structured this webinar to inform the construction industry on the tools to improve the performance gap. Now, I'm an architectural technologist and a building surveyor by qualification and by experience. So these slides are a little skewed in that direction, but the message is relevant to everybody. Also, as is the theme of Collabed, I've calibrated this webinar for early career construction professionals. So some of the information on these slides will be familiar to those who have a little bit more experience in the industry, but the stuff in the middle and the stuff towards the end should be new to most of you. So what's this webinar all about, and what will you learn today? So this is the contents page, and this will reappear at the start of every section to keep me on track and to let everyone know where we are. And I've got a wee note in the bottom right hand side to let everyone know what's coming up next, and a progress bar along the top to let you know how much more you have left to endure. Now you see those four little icons on the left hand side. Well, if we relate this knowledge exchange webinar to the content of our 4 research and industry support themes, then this content will fall under our sustainable design and building performance themes. Now, we have an article on what sustainable design means on our LinkedIn page, and we've got one coming up soon on building performance, which will arrive later in the month. So we're going to cover who are these building research solutions people, because we are relatively new. What is the performance gap and the sustainability parameters that I'll be talking about. As designed, standards and targets, tools and lessons from our experience with as built, and also a little bit at the end about our sustainability competition that we're sponsoring for Collabed, and I'll bring my colleague Jade in there at the end just to give a bit more context on what that competition is all about. So just to reassure you, there's nothing salesy in this webinar. The core of Building Research Solutions is knowledge exchange for the betterment of our built environment and the people within it. But I want to give you all a little context as to why we have the authority, so to speak, to be giving this type of presentation. So as some of you will know, Building Research Solutions started life in academia in the School of Built Environment there at Edinburgh Napier University. The founders, myself and Ruth, were research fellows rather, and lecturers that worked at the Scottish Energy Centre within the renowned Institute for Sustainable Construction. Now, we contributed to a lot of R&D work, which led to winning the Queen's Anniversary Prize for Acoustics and Timber Engineering. Now, I've been working in the field of AT, architectural technology, building physics, energy ergonomics, and human factors since about 2007. Back then, I was at the forefront of the R&D work that underpinned the knowledge on energy use behaviour, smart in-home displays, building performance evaluation, retrofit of historic buildings, and numerous different technical journals and articles and webinars and things like that. Ruth specialises in carbon reduction strategies, including her work to designing, developing and prototyping an innovative solar water collector. And more recently, Ruth has delivered content to enhance the understanding of the circular economy principles and life cycle assessment for modern methods of construction. So these are the areas that have influenced the research themes and the services we provide at Building Research Solutions. So an example of one of our past projects is this, the low carbon volumetric home project, which was equally the best and at the same time the most stressful project that we were ever involved with. As energy, building performance and sustainability researchers, it was exciting to be part of a project where a modern method of construction was being trialed along with the first attempt to achieve the highest targets on a particular sustainability standard. We didn't design the buildings, but we set the baseline as design targets used within SAP, the standard assessment procedure calculations. Now, the values that we had in there to hit that sustainability standard, they were tight. They were very tight. As in the women and men on the ground had about a 5 to 7% tolerance to get the damn thing right. The margin of error was really tight on that, and that's where sustainable buildings have kind of got to. Now, once built, we went back in and measured the as-built performance of the dwellings and the fabric energy generation and heat recovery technologies. And geez, those measurements were well off. I'm talking way off here. So far off that we stayed in the office for the entire weekend to rerun and rerun the data from our loggers and sensors just to make sure that we absolutely were seeing what we were seeing, because we did not want to report what we found. Now, at this stage, the occupants were literally days away from moving in, and these homes were very heavily advertised as being super cheap to run. Now, we had a couple of options. One, we could burn the data and flee the country, which was seriously being considered, or two, quickly produce a workaround strategy. Now, I produced the first ever quick start guide video to influence energy use behaviors, which is a very good way to help to curb any big fluctuations in the performance gap. And my colleague at the time produced details for added installation. But a lot of that was very much predicated on what we found after it was built, and we didn't wait until the occupants went in and started complaining to us 3 or 6 months later, or even up to a year later when the energy bills start rolling through. So I doubt that anyone has faced, and I hope that no one has faced, the performance gap meltdown crisis that we did back then. And that's what really influenced this particular presentation, which brings me nicely to the performance gap, why we should fear it, and the sustainability parameters that we're referring to here. So now this is not the first time that I've presented on the performance gap. And it's just getting my clock over here so I can see the time. This is the first time that I've presented in the performance gap, and I'm sure that you've heard a bunch of other people harp on about the performance gap. And I won't be the last person to cover this, because we're not quite done yet in terms of knowledge exchange and educating various different parts of the sector. And just because it's been talked about a lot doesn't necessarily mean that early career professionals know anything about it. And that's what we're here to do with Collab today. So the performance gap terminology, it didn't start in the construction sector, and it's not unique to us in any way. It was coined in the 19th century as a means to describe the reasons why the second generation of steam train or steam locomotive wasn't performing better than the Gen 1 train. And they needed a pretty good reason as to why all that investment in that technology wasn't actually providing a betterment. So we got the performance gap. Now, for us in the construction sector, it really boils down to three things. One, behavior. Two, the quality of our models and the simulation formulas. And three, the quality of our measured data in terms of what we get from our as-built sensors and loggers. Now, from behavior, what I mean is the behavior in three ways. It's the behavior of your design team, it's the behavior of your construction team, but also, and almost just as important than all the other ones put together, is the behavior of the people that occupy and use the building. So what makes this webinar different from the last one you've attended about the performance gap? Well, this is not about the why. This is not about performance gap, why the performance gap is a problem and the why sustainability is important, because we're well past that point. It's not about the how. How Performance Gap is racking our sustainability progress, because we're also well past that point. I've structured this presentation today to be about the what, as in, what does this look like on the ground? When you're in the trenches on the front line, when you're facing down the barrel of a very angry client, and you're wondering, what the hell am I going to do? That's what this particular presentation is about. So I want to focus on what the standards look like for as built, or as designed and as built. What does the measurement apparatus look like when you're doing it at the as built stage? What do all these numbers mean for as built and as designed? What do the units of measurement mean? And what do you get, what do I have to do to get it right first time? And what do I have to do to get it right next time? So let's get stuck into what the standards look like. And first off is sustainability, quite a broad term, a very big word with hundreds of meanings and literally hundreds of interpretations. The word is frustratingly difficult to actually nail down into something quantifiable. Now, conscientious citizens have been trying to define sustainability since the 60s, essentially to undo all the damage done by the rampaging Victorians during that era. Government stepped up in the kind of late 90s. Companies and corporations had joined the movement in the mid 2000s, or early stage of the 2000s rather, and now it applies to almost every aspect of everything that everyone does now and forever. So let's define our meaning of sustainability parameters for this webinar. Now, it's not about the three pillars, which is economy, environmental, and society. Now, my colleague Ruth could speak about this for hours, and she has an article on the LinkedIn page speaking a little bit about this. So it's not about that it's not about that definition, those three pillars, because that's much too high level for the purpose of this webinar. I'm talking about this one here on the right hand side, which we call the three actionable parameters. Now, these actionable parameters can be applied to water use, well-being, which encapsulates the term for acoustics or noise, and safety. It can apply to energy consumption, it can apply to carbon emissions, and it can apply to cost to run a building. So from this point forward, I'm referring solely to energy in buildings. And to keep it simple, I'm going to speak about space heating energy only, because the full version of this is about 150 slides, and we don't have time for that today. But if we can come back sometime in the future, we might be able to do these other bits and pieces with Collabed in the future. Now, the technology and the building parameters, those two circles there on the right-hand side, were the original actionable parameters defined between 2005 and 2007. Now, my research between 2007 and 2009, amongst others, introduced this third parameter, which is the occupants. Now, until that point, we were all happy in the notion that sustainability in the built environment meant optimizing the relationship between how much energy a building demands and how much the on-site renewable energy technology could supply, or in other words, reducing one and maximizing the other. Then we understood that almost every house had different electricity, non-heat related appliances. So there was an easy solution for that. We simply changed the definition of sustainable buildings so that it no longer includes unregulated electrical appliances, and it only includes energy for space and water heating. Then we started to see our new shiny, low carbon, low energy buildings behaving very badly with huge energy bills. Not so easy. This was not so easy to resolve because now humans are involved, and nobody went to architecture, surveying, engineering, or construction school to learn about why humans do what humans do. So psychologists got involved, and that got very messy for those of us not from a psychology background. But we're not going to worry about that today. We're going to focus on the materials side. So if we look a little bit deeper into these three actionable parameters, we have materials, which for this purpose of this webinar is focusing on thermal transmittance, thermal bridging, and condensation. It also includes the embodied energy, which we're not going to cover today. Technologies focus on space heating generation, which is really about the fuel type and the coefficient performance, ventilation strategies, and also heat recovery systems. And human expectations when it comes to space heating is energy bills, natural light, air quality, noise, safety, and what you can do to the building after it's been constructed. Now, if we look at that Venn diagram just a little bit closer, we realize that the new parameter of human expectation not only brings a lot of challenges by itself, but it also introduces two more gray areas, which between human expectations and materials is perceived comfort, which has a very broad spectrum. Between human expectations and technology is usability and controls, specifically those of the user interfaces we have to interact with to achieve our perceived level of thermal comfort. And then we have the age-old performance optimization between technologies and materials, which is relatively easy to achieve. Now, as we got our heads around the right behavior modification and change stimulus, we realized, hold on a minute, why is a low energy house made with steel and phenolic foam declared as being just as sustainable as a house made from timber and sheep's wool? Why is that being allowed? Then the economists came in with their carbon accounting, embodied energy, and life cycle assessments, which expanded the scope of sustainability and the parameters past the operational phase of a building's life. And that's a whole new field of science, one which my business partner Ruth knows all about, but one which I'm going to avoid talking about today. For this webinar, I only want to cover one of these parameters in isolation, and that is fabric first, the materials. So, and by fabric first, I mean specifically the performance indicators for U values, air permeability, thermal bridging, condensation, and energy consumption. Now, I want to look at these five variables through the lens of standards, targets, values, units of measurement, and then after that, the apparatus and equipment we can use to actually measure them when the building is complete. Which brings us neatly into the design standards. Now, we're all familiar with this little adage, and it's flexible enough to be applied here. So I want to keep this in mind as we go through these next set of slides, because this is what typically happens. Someone will say, oh yes, air tightness. I know all about air tightness. I've read something about that in a trade magazine on a CPD pull-out one afternoon. Well, first off, it's pronounced air permeability, not air tightness. And secondly, variables like air permeability are set way at the very start of a design stage, and then can very quickly get lost in the myriad of other important design and building requirements. And no one really pays much attention to it until your building performance contractor comes back with a report saying your air permeability value is much worse than you said it was going to be. What are you going to do about it? And then there's lots of running around and getting a bit panicked. Now, a lot of what I'm talking about in terms of U values and air permeability, etc., has become so ubiquitous to us in the built environment that it's overlooked an awful lot and just perceived as, well, it'll be all right in the night. We'll get it sorted out when the time comes. And people can lose focus on those things very quickly. So when I say sustainability within the context of this webinar, again, I'm referring solely to fabric efficiency of the dwelling, and I'm going to go through each of these five one at a time. Now, some of you will be familiar with where those variables live in the devolved building standards or building regulations or building control documents, whatever you want to call them, from whatever region you're from. But for the sake of completeness, let's give each of these variables their proper origin and their legal position. Each of them exists in at least one BSEN ISO. And I want to point out that all of these are part of legal requirements for building standards or building control, whatever you refer to them as, and have been and need to be verified by the building standards or building control officer before the thing is actually built. So what you read inside Part L or Section 6 or Part F or wherever else, they've all begun life in one of these BSEN ISOs. And most of them have been renewed in the past 3 or 4 years, and they will continue to be renewed and will continue to inform BRE, or BRE will continue to inform them. That will continue to inform SAP. So as we move from SAP 2012 to SAP 10, there'll be a jump from the BSEN ISO 13790 to the BSEN ISO 52016, which has a brand new set of formulas and equations there to define thermal bridging. So that's where they kind of come from. Now we've got some non-compulsory, some voluntary standards here, which are Passive House, Code for Sustainable Homes, Eco Homes, and Scottish Building Standards Section 7, appropriately named Sustainability. I'm going to make reference to Passive House and SBS 7 once or twice moving forward, and I want to make clear that those are voluntary standards. Now, I'm not going to go into the Code or Eco Homes because they're kind of either dead or have died off in recent memory. So first off, U value or thermal transmittance also includes a factor for repeated thermal bridging, which is one of the two types of thermal bridging I'll be speaking about today. U value is a measure of how much heat energy in watts passes through every meter squared of element when the temperature on either side of that element differs by 1 degree Kelvin, and that gives us our watts per meter squared Kelvin. And this value has the largest effect on the thermal comfort within the dwelling, or any building really. So if you have, which happened recently unfortunately and got a little bit of unfortunate press coverage in the construction news, if you have a house builder that misses out a big chunk of wall insulation for whatever reason, it doesn't take too long before the occupant works out that, oh dear, this room is very cold. Why am I paying this amount of money for a new build? So it's one of the ones that are very easy to detect by an occupant in terms of it's not being there or not working good enough. Now we use the BRE U value calculator and the BuildDesk U software to do our at design stage calculations. For existing buildings, the U value can be as high as 5.2 for windows, 2.4 for a roof, and 1.8 for a wall. They're historic values, kind of pre-1919 buildings. For new build, the targets in the various different building standards, regulations around the country goes between 0.21 to 0.3 for walls, and very similar for roof and floors, and 1.6 for openings. And the Passive House standard is somewhere below 0.8 for openings there. Now, the mystical quest to find and capture the mythical unicorn U value is well over. Now, we have found the mythical U value unicorn, and it's out the back eating hay, and it's living happily. U values of 0.2 aren't getting any lower, at least from a regulatory perspective. You're not getting any lower than 0.2. The lowest that we have ever seen and that we have actually measured in situ is 0.09. Now that wall was almost 500 millimeters thick and had a very healthy dose of aerogel everywhere you could conceivably imagine. Aerogel being one of the best materials for its thickness to lambda value thermal conductivity. It almost made me cry to see somebody trying to screw a shelf into that wall. It was such a piece of perfection. So we're not getting much better in terms of where U values are going for buildings for as design stage, but you can get it a bit lower, but you're going to pay for it. Thermal bridging, or the psi value. Now this has the largest effect on the health of the building and therefore the health of the occupant, which we'll cover a little bit later under condensation. Now, we use Flexo or the LNBL Therm software, the Therm software being free and the Flexo one having one of the better, more usable interfaces, but there's a cost to that as well. Now, this is the lesser known thermal variable than its cousin, the U-value unicorn. And until recently, designers were using the default value that SAP would give you, a little tick box there that allowed you to use a default of 0.15 watts per meter squared Kelvin as the Y value. And then you multiply that by the total surface area of all the elements in your building, and then you get that in watts Kelvin, which is called the transmittance heat transfer coefficient, HTB. Those days are gone, and we can choose BRE's default psi values for junctions, which are, for example, a junction between a wall and a floor is 0.32 watts per meter Kelvin, or for a windowsill, 0.08 watts per meter Kelvin. Or you can use the accredited values, which can almost be half of those default values, or you can use Flexo or Therm and design your own values, which can again be better than those values. And you can provide evidence to building standards or building control, however you want to call them, and that will be pretty much accepted. We'll cover an issue in designing your own thermal bridging details a little bit later towards the end. But ultimately, as U values have become really low and almost impossible to get much lower, the effect of heat loss through junctions has become the new obsession of the built environment and the new obsession of the building performance sector, which has seen a large increase in the number of thermal bridging software available, and also quite a large increase in the cost of thermal bridging software, which I'm sure you'll look at when you go to some of these software and go to buy now, and then you pick your jaw up off the floor. Next up is air permeability, and same is true here with super low U values. The effect of heat escaping as ventilation, heat loss, is very significant at this stage. Now, air tightness, air permeability is a product of, air tightness is a product of achieving low air permeability or low air changes per hour. So air tightness is a product of achieving low air permeability, and that's how BSE and ISO defines it. So what's the difference between air changes per hour and air permeability? Well, air changes per hour is the measure across the building's volume, and air permeability is per the envelope area across the building envelope. So what does this look like? Well, unless you're working to pacify standards or other non-British standards, then you're going to have to use the term air permeability. And the unit of measurement for that is the airflow in meters cubed moving from inside to outside of a dwelling every hour through every meter squared of the building's insulated envelope. And importantly, at 50 pascals. So let me give you a bit of context there as well. On a relatively breezy day, your building's pressurized between 5 and 10 pascals. So when you're doing your air permeability testing, you have to stress test the envelope at 50 pascals. So air permeability numbers are things that is a number that's been more commonplace in the vocabulary of the building sector, and it's a number that can also be poorly understood, and people certainly from the heritage sector can jump onto and start to bash at sustainability targets for air permeability values. One thing I want to make clear here, I'm not going to go into any more detail, is air permeability testing is a measure of the unregulated ventilation heat loss through the building. When you're doing that test, which we'll talk about in a second, you seal off all the other parts of the building that's designed to be there to regulate the indoor air quality. That's your extractor fans, that's your trickle vents, everything else. So this number, this air permeability number, should be as low as physically possible, because whenever you finish your test, you remove all the sticky tape from your vents and from extractor fans and from the trickle vents, and the building's going to breathe nicely. So this number should really be as low as possible. So be aware of that if you're in the heritage sector. I've added a little quick and dirty at a glance value here, because we don't really have a software to predict or to calculate air permeability value. So this comes from our experience that we have measured loads of buildings in the past 13 odd years. So a measurement of 22 is the worst that we've ever measured, and that came from a pre-1919 building. No, I tell a lie. That came from a building built in 1955. The building was quite poor. You tend to find that post-war, before the big oil crisis in the 80s, even though we had an oil crisis in the 70s and a coal crisis in the 80s, even during the oil crisis in the 70s, buildings were still being built quite poorly. And it wasn't really until the coal crisis in the 80s that we started paying attention to things like unventilated pathways, and we gave up on silly methods of construction like concrete frame and no fines concrete. Now, 15 meters cubed per hour per meter squared is the backstop for most building standards. 10 is roughly where a pre-2007 dwelling can get to, with a bit of retrofitting. 7 is the value that SAP uses for its target emission rate. 5 is a threshold between natural and mechanical ventilation. So if you're designing a building to have a value over 5, you can sleep happily in the knowledge that the trickle vents and the window opening behavior will cover indoor air quality. But if you go below 5, then you need to have a positive form of mechanical ventilation. And that's for those days whenever the building is being depressurized by wind direction, wind speed, and there's no air changes coming in through natural ventilation, like trickle vents and opening windows and things like that. We've all experienced in your building where it's blowing a gale out the front of your house, but you're at the back in your study and it's absolutely boiling, and you open a window and nothing happens, because the front of the house is being positively pressurized and the back of the house is being negatively pressurized, which means no air movement on that side of the house. So if you get below 5, you need mechanical ventilation to destratify the air and maintain air quality. 3 to 2 is pretty much typical for construction after 2017. 1 is tricky but super doable, just like that 500mm wall for a U value of 0.09. It's tricky, but it's doable. And 0.6 is one that is very difficult to achieve, and one where everyone involved really needs to give a crap what's happening with the construction of that building. Now, I've put 0.6 meters cubed per hour per meter squared at 50 pascals here. And those of you anointed in the religion of Passive House will say to me, that's not air changes per hour, John. That is air permeability, and it's different. Well, yes and no. When your building is a very geometric cube, like most of our houses are, then the conversion from meters cubed or from air changes to air permeability is pretty much 1-to-1. When your building has very complex geometry, then those numbers do differ. But for the purposes of this, and we're talking about simple structures for now, it's 0.6 for Passive House. Next up, condensation, and this will take 2 forms: surface condensation and interstitial condensation. Now, not an easy word for me to pronounce, interstitial, but essentially means the condensation that forms at the interface between the layers of an element, like a wall. So between your insulation layer and, say, your OSB on the outside, which is there for racking strength. Now, this has the largest effect. This also has a large effect on the health of the building, which affects indoor air quality and therefore the health of the occupant. We have a few metrics of performance here. We have ambient relative humidity, which must be kept below 70%. Surface temperature, which is calculated as surface resistance temperature factor, or FRSI, and the dew point or temperature pressure differential. Now, with prolonged instances of RH over 70% and/or areas of an element where a cold spot exists, also known as a thermal bridge, then there is a high likelihood that mold will germinate, grow, reproduce, and as such, then spores will begin to enter the airstream within the building, leading to respiratory issues for occupants and then ultimately damaging the more vulnerable building materials like plasterboard, wallpaper, timber battens, lath and plaster for older buildings and things like that. Now, interstitial condensation occurs as a result of the temperature dropping through the element as the air moves from the inside to the outside, and the air loses its ability to hold water in its vapor form. It condenses, becomes liquid, and then it can dampen things like wool or soft insulation, and then it can allow for corrosion or mold growth on metal or timber elements. So the important thing here is that those two lines that my orange arrow is pointing to, those two lines in that glacier diagram on the right-hand side, they should never meet or cross. And I'll resist the urge here to use a line from Ghostbusters for those two lines. So we use BuildDesk U software for our condensation risk analysis. Like most other software mentioned so far, it is a steady state and mostly numerical input. Woofy, which some of you may be familiar with, is the antidote to those steady state type of numerical software. However, there are known issues with Woofy in terms of the weather file for regions of the UK and also material library databases for the common materials we use in the UK. So I'm not going to show what Woofy looks like at the moment. So next and finally within this is the energy consumption. So essentially this is the combination of every other variable we have just spoken about. Now, you won't find actual kilowatt hours per year targets in most standards or regulations. Most of them leave that to the somewhat useful target emission rate set by the BRE SAP methodology, the Standard Assessment Procedure methodology. Now, I take issue with using carbon emissions as a key performance indicator. After all, energy as joules or kilocalories or watts is an absolute term. It makes up everything living in the universe and describes scientifically the flow of energy transfer, whereas carbon values can be changed almost instantly whenever the national grid turns on a backup coal or oil-powered power station during a particularly interesting episode of Coronation Street or something like that. So carbon can change instantly where energy is absolute. So TER, not really on board with that idea, but it is what it is. But Scottish Building Standards Section 7 and Passive House aren't afraid to set a kilowatt hour target. So the Scottish Building Standards Section 7 have that somewhere between 20 and 40 kilowatt hours per meter squared per year. And Passive House has that at 15 kilowatt hours per meter squared per year, or their 10 watt peak per meter squared for whatever energy system you're using there. Now, I want to, again, just like air tightness values, I want to give a bit of context on what those numbers mean. So I've got a table here, which again is measured from the many years that we have measured buildings. So a house or a flat within the gold and silver standard for Scottish Building Standards between 20 and 40. Houses that we have measured that were built between 2007 and 17 were coming in between 28 and 145, and houses that were built between 1750 and 1920 ranged between the 132 to 215 kilowatt hours per meter squared per year. So not a terribly easy thing to achieve in the first instance. But if you are focusing on those 5 variables above, it can very much be done at design stage. Now we use, like everyone else, we use SAP software. Stroma provides ours. But we also use Energy Plus with the Design Builder graphical user interface as our dynamic energy modeling software for times when we need significantly more control over the weather files and over the occupancy schedules. Right, so almost finished, got a couple more slides to go, and then we'll hopefully have a bit of time for Q&A if there is any. So that's us covered the as designed standards, the targets, the 5 major variables, what they look like, and what they're all about. Now I want to move on to the as-built tools that we use and the oh, got a little pop-up here. As-built tools and lessons for the same 5 variables we just spoken about. So just like the as design standards, good old reliable BSE and ISO have a set of standards for measuring these variables after the building is constructed. Now, you're going to say to me, John, what are those question marks for? Well, that brings me to another point I want to make. 13788 is actually the standard for measuring or for calculating condensation in buildings. It's not actually used for measuring condensation in buildings. However, we have reversed engineered that standard and created our own methodology from those principles in 13788 for how we measure condensation in buildings and within elements of what makes up a building. And 16247 is more of a good luck message from BSI as opposed to how you actually do it. And again, we have used that in our 13 years of experience to develop our own methodology for energy monitoring. Now, ultimately, a big takeaway message here is you can measure whatever you like, however you like. And a lot of it does come down to how much money you have to spend on your own hardware and software, or how much money you want to throw at a consultant to do these sort of things like us. Now, what's important there is if you're kind of doing a DIY thing of your own, the important thing here is that whatever you're measuring, make sure you're getting results that from accuracy and precision perspective, but also from a unit of measurement perspective, can be directly compared to what you have produced at the design stage. So let's have a little look and see what those are. So these are quite quick, these slides. I know I'm running out of time. So I'm going to follow the same format for the next 5 slides for U-value, thermal bridging, air permeability, etc., etc. I want to give you a bit of an image roll here along the bottom as to what they look like, and we have them used and we're installing them, and a little bit of what the output looks like from our reports, etc. But I want to just very quickly cover the apparatus, the methods, and the outputs. So the U-value measurement is has quite a long monitoring period, but it's by no means the longest. But because it has a greater than 14-day monitoring period, that's kind of one of the main reasons why it hasn't made its way officially into any building standards. And also, it can be a little bit destructive when you're trying to pull your heat flux mat off the wall and you've got either wallpaper or paint there. It can be a tad destructive. So that also has kind of taken away its charm a little bit. But the output from that is in volts per watt per meter squared. Then we have algorithms that turns that into watts per meter squared. And then we declare that as an absolute value after the data becomes isentropic, which means it becomes steady state. Now, there is, no matter who gives you a measurement from U-value monitoring, there is a plus or minus 10% error on this type of measurements. So you can get a number, watts per meter squared Kelvin, and you can compare that directly to what your U-value software told you it was going to be, but be aware that there will be an error of at least 10% on your measurement. And whoever's giving you that number should report the size of the error. Now, the larger the temperature difference from inside to outside, we're looking for at least 10 degrees, the larger that temperature difference, the smaller the error, but you're not getting much less than about 5%. Now, if you have a very small temperature difference between inside and outside temperature, the error can be as high as 20 or 30%. So that's something to be aware of. IR, everyone's favorite piece of technology for measuring buildings. and erroneously described as easy to use and often very poorly interpreted. But it makes for really cool images, and these are what we call thermograms. Now, they're quick and they're cheerful, and they can be used to compare to your thermal bridging results from your software, specifically the temperature points along your internal surface of your computer model. But only if your software, your camera and your IR software supports radiometric data. Now, radiometric data will add about £1,000 onto the price of your camera, and you tend to not get radiometric data at the £200–300 camera size. Now, radiometric data is important because every single pixel that you see on your thermogram has a temperature point, and that temperature point can then be used to compare to the temperature point on your thermal bridging software, and that can then give you the comparable number that you need. But for the most part, this is mostly for qualitative findings and for detecting cold spots, air movements, moisture buildup, and things like that. Next is air permeability, and it's often incorrectly referred to as air tightness testing, but that's how our building standards call it. And it's a very common test within most housing developments. And you drive past a certain housing development at a certain point, you're most likely going to see one of these red doors popped up with a fan in it somewhere. Now, it's a balance between the speed of an IR survey, which can be minutes to hours, and the high quality quantifiable results of a U-value measurement, which can take up to 12 days to get that number. Their air permeability is favoured amongst most building standards or building regulation committees because it can be quickly done and it gives you numbers that you can rely on. Now, the thing you need to be aware of here, if you're ever looking at an air tightness result, is that there are two major factors that are reported, or numbers rather, that are reported alongside with the result. And that is the coefficient, the correlation coefficient, and the expondent. Now, there it indicate a margin of error. Now, these air tightness tests are really only precise up to 1 decimal place, and they can have up to 15% error. So if your air tightness person comes along to you and says, listen, we've measured your building and your building comes in at 3.247. Well, no, it really came in at 3.2 because it's only really reliable up to 1 decimal place. And there's a margin of error in there as well. And what you also want to see on your report is the correlation coefficient, which has to be higher than 0.98, and your expondent, which has to be between 0.5 and 1, because you can get a result from an air permeability test where you hit your target, but your expondent is way off and your coefficient is way off, and it essentially means that number means nothing. So if you're ever looking at a report on air tightness or air permeability report, please look for those two numbers. Almost near the end, last couple of slides here, condensation. Now, this really needs a year's worth of monitoring and measurements, but 3 months would be a minimum if you were trying to push something through quite quickly. And if it was a 3-month monitoring period, then you're looking at doing that over the heating season, which is called the winter period, which is essentially the coldest months in the UK is December, January, and February. So to expedite those types of results in a very short monitoring time frame, you're looking for times of the year whenever the external relative humidity is high and the temperature is low. And again, that's December to February. So ultimately, you want temperature and RH data from your measurements that can be compared to the outputs of your software. Now, if we're looking at the outputs from BuildSQ, for example, and then the outputs there, according to BSE and ISO 13788, is monthly. So if you can get measured data monthly, then you can then compare that to what you calculated monthly, and you can measure the difference there and what's going on. Finally, within the variables is energy consumption. and the output, just like the BuildSU software for condensation, the output for SAP in terms of energy consumption is monthly. That's the lowest resolution, or sorry, rather the highest resolution you're going to get from SAP for that. So you want to measure at least monthly, but a year is really the minimum that you're looking to get from that. So you'd be measuring volts and amps and turn it into kilowatts, and you average that over an hour, you get kilowatt hours, you get that for electricity, and then your pulses connected to your gas meter are converted to meters cubed, that's converted to kilowatt hours, then you get a month and a per year thing. Now you can get little cheap and cheerful things off the shelf for like £5 or £10 to measure electricity, but they just measure amps. They don't also measure volts. Now, if you just get one that has a little blue current transducer there, and that'll just measure amps, it won't measure volts, and that leaves you quite exposed to getting a margin of error of up to 25% if you're just measuring amps. You really want a piece of hardware that measures amps and volts. Now, final two slides. And I know I'm a little bit over time here, but I'm going to move through these quite quickly. So we're going to wrap this up, and no better way to do that than to go over some of the lessons that we have learned over our experience and the actions on how to close that performance gap and help on your next project. So let's go through these 5 variables very quickly. So for U-value, from learning from as built and going back into the next generation of building you're working on for as designed, you're looking for either thicker insulation, so if it's a timber frame, you're looking to go from, say, a 140 millimeter to, say, a 220 millimeter, but you also could invest in insulation with better lambda values. Thermal bridging, you're looking really at adding insulation between the structural element, like your timber junctions around your roof eaves, things like that, and either internal or external environment. But what's important here, what I alluded to earlier, is to make sure that wherever you're putting that additional layer of insulation around a structural element, make sure that somebody can actually get their hand in there to actually install that piece of insulation, because if they can't do it, they're not going to be able to get that, and then your thermal imaging camera survey will give you a bit of a hard time. Air permeability really is come in the form of additional air tightness layers, which is tapes and membranes around junctions and openings and things like that. Condensation, it's about knowing the difference between your natural and your synthetic insulations in terms of the vapor resistivity, looking at that all-important vapor resistivity value on the manufacturer's data, and also being aware of what vapor control layer does what and where it should go. Energy consumption, once you get those 4 right, for energy consumption, all you can really do after that is develop quick start guides to help the occupants understand how to use this new high-tech building, which can often look like a bit of a spaceship whenever you look at all the different gizmos and gadgets and interfaces and controls you have, and in-home display, which is written into the Scottish Building Standards Section 7. So finally, how to implement all of that into your workflow. So we have structured our research themes and our whole company around closing this performance gap for enhancing and safeguarding sustainability. And we find that the first and most challenging gap to close is the knowledge gap. Once you close the knowledge gap, then you will inherently close the performance gap. So it's about monitoring, testing, capturing the data. So the things that you want to be thinking about is questioning your manufacturing data, because most data you get from most manufacturers will come from laboratory tests, not from in situ as used tests. So those numbers inherently are always going to be slightly different. So trust in case study examples. Get your own hardware or become very friendly with a building performance evaluation company, or get your own hardware, then get your own data. And what's importantly there, if you work with a if you work with a building performance company, or you work with your own hardware and your own data, build up your own data sets, build up your own databases, and replace all those values that you thought you had from the manufacturer with actual values that you've got from case studies or from doing your own testing, wherever that may be. So we did start a little bit late, so I hope I'm not too far over time. But that is all that I have time for today. And there's lots more beneath that and lots more around that, but that's possibly for a different webinar session. So before I hand back over to Alex, I want to do a quick promotion on one of Collab's next ongoing competitions. And I also want to hand over to Jade in a few seconds. So if nothing else, I really hope that you enjoyed the presentation and you found it somewhat interesting, and that you have at least a little bit more depth of knowledge around the performance gap and those sustainability parameters. Now, you may or may not have seen this competition that we are sponsoring and Collab are promoting at the moment. There is a sign-up sheet. It's a bit different to how the last competitions were run in terms of it's a bit of a closed thing until the very end. But we're looking for entrants, for applicants or for people to get involved with this competition to design a particular type of building, because we want to get you involved in this conversation around sustainability, and we want you to set your own sustainability parameters, and we want to help you to focus your mind to help produce something that you could add to a design portfolio or to a CV or to your next interview, which is really what Collab is all about. So I'm going to hand over to my colleague Jade just now to give a little bit more detail on that competition. Jade, are you there?
Yep.
Super. So over to you, Jade.
Okay, thanks. So everyone, just as a sort of overview, we're looking for an A1 size page of content. We've suggested a template on the brief, which you can find in the Collab's LinkedIn page, and you can use that as a guideline. Although there are opportunities for cash prizes, it's important to note that regardless of who wins what, we at Building Research Solutions want to give you the opportunity to focus on creating something that will enhance your CV and portfolio, as John's saying. If you don't win the cash prize, we'll be allocating feedback anyway, and if you do win, then that's a happy bonus. You've got till Sunday the 3rd of January to submit your project to us via email. It's important for me to highlight as well that this is different from the previous Collab competitions. We're not looking for the best renders. We're also not looking for fully detailed technical drawings or energy calculations. Obviously, I really recommend getting involved, but if you've found yourself with some extra time in your hands due to COVID, it's definitely a good idea. And regardless of the outcome, you're still going to benefit one way or another from entering. For the full competition brief, visit the Collab's LinkedIn page. If you go to posts and documents, it's in the PDF format where you can slide along and see the full content and what's required of you. As John says again, there's a sign-up sheet on the original post, so we ask that you put your name on it beforehand. If you're struggling to find it, we will be resharing the post again shortly. If you have any questions, feel free to message myself or Alex on LinkedIn. And finally, we're really looking forward to seeing the entries. So thanks very much.
Superb, thanks Jade. So I'm going to hand over now to Alex. So Merry Christmas to everyone from Building Research Solutions. So Alex, sorry for breaking your time limit there, but we may have some questions. I'm happy for you to kind of...
Yeah, well, I'll stop the recording now, and yeah, thank you very much for John and Jade.